Hey guys, what's up? Welcome to day 11. Today we'll be working on the chain rule. The chain rule is the derivative rule that we use on compositions of functions. So just a reminder on compositions of functions, right? If we take a look here, it says let h of x equal f of g of x, right? We're used to solving compositions in Algebra 2, maybe even Algebra 1 in pre-calc. And today we're talking about how do we do derivatives when we see a function, g of x, within another function, f of x. Okay, so here's how this works. If h of x is f of g of x, then h prime of x would be this. It's going to start with the derivative of the, right? I like to call this the inside function and this the outside function, right? And h prime of x then would be the derivative of the outer function. Get used to this way that I'm going to phrase this with respect to the inner function. So it's not f prime of x, it's f prime of g of x. And then we multiply. Don't forget, I always say, don't forget to chain on the chain rule. We multiply by the derivative of that inner function. So in this case, that would be the derivative of g of x, which would be g prime of x. Again, this is multiplication here. Okay. So again, chain rule here, we read this as the derivative of the outside with respect to the inside times the derivative of the inside. Okay. So those are the words that we're going to help try and make sense of here with some more examples and how this works. The chain rule is a, generally students struggle a little bit to grasp the concept of it and execute it properly. But the more you practice it, the easier it'll get. Okay. So again, just to show you that equation in one more form, let's say I told you g of x equals h of k of x. Then I know g prime of x would equal the derivative of the outside with respect to the inside times the derivative of the inside. So it's important to know it in its general form like this. I mean, we've seen that with product rule and quotient rule. It was helpful to be able to do it with our function notation, okay? But it's also going to be important to be able to solve it within the context of specific problems. So here's example 1. Okay. Let's let f of x equal cosine of 8x squared. So if f of x equals cosine of 8x squared, we're supposed to find f prime of x. Now, if this question was just cosine x, that would be a derivative that we have memorized. We know the derivative of cosine x is negative sine x. Okay, but because we're doing cosine of this other function that is something other than just regular old x, we have to use the chain rule in order to solve this. So I like to, I'll write this out now. When we get good at this, we're not necessarily going to write this out all the time, but it's good to think about this. I want you to think of the inner function here and our outer function here. Okay. If I wanted to write this as a composition of two functions, I might say, let's use h for the inside. If h of x was the inner function, 8x squared, and g of x was the outer function. In this case, it would be cosine x. But if I wrote g of h of x, that would read g, which is cosine, of h of x of 8x squared. Sorry, kind of got cut off there. 8x squared is our inner function. Cosine is our outer function. Okay, so let's start talking about this, and I really want to focus on that word with respect to the inner function. So finding f prime of x here, I would simply do this. So I want to think of my outer function as cosine of x, okay? So I think about what is the derivative of cosine of x? Well, I know that's negative sine of x. But I don't want to do the derivative of the outside with respect to x, okay? I want to do the derivative of the outside, negative sine, with respect to the inside function, which is 8x squared. Again, it's like I'm doing the derivative of the outer piece, but keeping this inner piece the same. Okay, that would be g prime of h of x, right? Or if we think about it with f and g up here, it'd be the derivative of the outside, negative sine, of the inside, 8x squared. Okay, but the chain rule is not done yet. I now have to multiply by the derivative of the inner function. We're going to multiply by the derivative of that inside function. The derivative of 8x squared is a simple power rule. That would be 16x. And here I have the derivative of the outside with respect to the inside times the derivative of the inside. Now I'm going to take a second to clean this up. Generally, we write polynomial stuff first, then trig stuff second. So this would, if this was on a multiple choice, it'd probably show up as negative 16x sine of 8x squared. Okay. Derivative of the outside with respect to the inside times the derivative of the inside. I'm not going to join the 11th grade meeting. Okay, let's try another example. So here I see a composition of two functions. I see the function 4x cubed plus 2. This would be identified as my inner function. And my outer function would be x to the 4th. Okay. Now we don't see the x, right? But we can think of the function x to the 4th, right? It's like stuff to the 4th power. We think of it as like x to the 4th as our outer function. And our inner function is 4x cubed plus 2. So when I compose those two, when I make a composition, if f of x is x to the 4th and g of x is 4x cubed plus 2, then f of g of x would be 4x cubed plus 2 to the 4th power. Okay? So anytime you see parentheses with a whole thing raised to a power, that's going to be code for we're doing a chain rule. Now I could do 4x cubed plus 2 times 4x cubed plus 2 times 4x cubed plus 2 times 4x cubed plus 2. And I could do the product rule 4 times, but that's going to get really awful. The chain rule helps us to do this quicker. I start with the derivative of the outside. And again, if my outside is like x to the 4th, I know the derivative is 4x cubed. But again, this is the derivative with respect to x. I'm not going to see 4x cubed. I realize now that I probably should have written, let me change this to a 5 just to make it. There's too
too similar. Sorry about that. So my outer function here is like x to the fifth, and I know the derivative of x to the fifth is 5x to the fourth. Okay. But again, I don't want to do the derivative of the outside with respect to x. I want to do it with respect to the inside. So here's how I think about it. Just picture this whole thing like a big x. What would my derivative be? Well, I'd take this 5 and multiply it up front, and I'd get 5 something to the fourth power.
What's important to understand here is that inside, right, is what we're doing the derivative with respect to.
So it should just be copied down as 4x cubed plus 2. This is the derivative of the outside with respect to the inside. And then I just have to multiply by the derivative of the inner function. Well, the derivative inside there would be 12x squared. Right? The plus 2 goes away when I do the derivative.
So there I have an answer of 5 times the quantity 4x cubed plus 2 to the fourth times 12x squared. Again, that's the correct answer. If it was a free response, you could simply circle that. Okay, on multiple choice, this would show up as f prime of x equals, I would multiply these two terms together and put them out front. 5 times 12 is 60. So we'd have 60x squared times the quantity 4x cubed plus 2 to the fourth. Again, you can think of it as stuff to the fifth, right? We'll have 5, keep that the same, right? It's f prime of g. Here's our g. Here's our f prime with respect to g times g prime. Okay? If you're a little confused, don't worry. The more you see this, the easier it'll become. And the more you practice it, the easier it'll become.
Try another one.
Okay, so let's say f of x is sine cubed of x.
Find f prime of x.
Now, this notation here, we're probably used to seeing it, okay, but it's important to remember what that means. When the 3 is written where it is, right, the AP exam loves to use that kind of notation, so we have to be comfortable with it.
We also have to know that that literally means sine of x is being, the whole thing is being raised to the third power.
Now, when you write it with this notation as opposed to this notation, it's much easier to see that sine of x is our inner, x cubed is our outer.
Okay, so here's my in, here's my out. So to do f prime, I'm going to do the derivative of the outer function, which will be 3 blank squared, right? I'm taking that 3, multiplying it out, and reducing that power by 1. But I have to do that with respect to the inner function, which is sine of x. The derivative of the outside with respect to the inside. That means sine x shows up in there. Make sure you're not doing the derivative of the inside. We don't do that yet until the end. Okay? Then I simply need to multiply by the derivative of the inner function, which I know is cosine x. Okay. So, cleaning this up a little bit, let's write it in the same notation that the problem was given in. And we can say f prime of x then would equal 3 sine squared x cosine x. That's likely the notation that would be on the final answer. Okay. Let's try another one. Okay, so when we see E,
E is usually a very nice thing to see because the derivatives are itself. Okay, except for if it's e to the x, we know the derivative of e to the x is e to the x. But when we see e to something other than just regular old x, that's where chain rule is going to come into play.
Again, what I identified here is this is my inner function. 3x cubed plus 1 is inside, excuse me, of our outer function e to the x. So to find f prime of x here, now I know the derivative of e to the x is e to the x.
I know e's derivative is itself, but I have to do that derivative of e with respect to the inside.
So the derivative of e to the x is e to the x, but I do the derivative of the outside with respect to the inside.
So this derivative starts out exactly like f of x.
Now I just need to multiply by the derivative of that inner function, right? I call it chaining on the chain rule. And we got to chain on that multiplication of the derivative of the inner function. Well, the derivative of the inner function is 9x squared, plus 1 goes away. Again, cleaning this up, this would look like 9x squared e to the 3x cubed plus 1. There is
A nice cleaned up version of that derivative using the chain. Okay. Let me show you another example. So here I see a function, right? What's the inside here? What's the outside? My inner function is tan x.
my outer function.
Is the square root of x. Okay? And once again, with square roots, it's important to think of them as raising to the power of 1/2.
So again, in your head or writing it out, you're going to want to rethink of this thing as tan x to the 1/2 power. Okay? So go ahead and try this one on your own. See how far you can get. All right, here's what it should look like. I do the derivative of the outside with respect to the inside.
That's the first part of the chain rule. The derivative of the outside, I'll take that half, multiply it out front, reduce the power by 1 to get to -1/2, keeping the inside exactly the same. Half tan of x to the -1/2.
But don't forget to chain on the chain rule. I'm going to multiply by the derivative of tangent of x, which is secant squared x. All right, cleaning this up a little bit. Again, if it's a free response,
Circle that. That's the right answer. This is more likely to show up on a multiple choice question, however.
couple of things.
I see that tan is raised to a negative exponent. So I'm going to drop that into the denominator.
There's already a 2 in the denominator right here. This one has a positive exponent, so it's going to stay on top. So on top, I'm going to have secant squared x. And on bottom, I'm going to have 2
times tan of x to the 1/2 power.
which I know means a root tan. There's a nice
Simplified version of that. Okay, let me show you another example. Let me make that an x squared. Okay, so if we're going to let f of x equal the natural log of 2x to the fourth plus x squared, I want to find f prime of x. Again, by now you should be used to identifying inner and outer functions. Our inner function here is 2x to the fourth plus x squared. Here's my inside. My outer function is ln x. And once again, it's helpful to know that the derivative of ln x is 1 over x, but I'm not going to see 1 over x show up here, right? That would be the derivative of the outside with respect to x. I want to do the derivative of the outside with respect to the inside. So f prime of x here would be the derivative of the outside, which is 1 over x, but it's not with respect to x, it's with respect to the inside. So there's the derivative of the outside with respect to the inside, 1 over 2x to the fourth plus x squared. And now I'm going to multiply that by the derivative of the inside. Well, I know the derivative of the inside is 8x cubed plus 2x. Now again, cleaning this up, I'm just going to put this on top. I'm going to call it 8x cubed plus 2x over 2x to the fourth plus x squared. Now you may be asking, can we simplify this further? The answer is yes. Take a look at the coefficients, 8, 2, 2, and 1. So I can't simplify coefficients because they're not all divisible, right? Whenever there's a 1, you're not going to be able to. But I do see an x cubed, an x to the fourth, and an x squared. All 4 of these terms have an x in them, so I can divide every x. I can divide one x out of each one. I can call this 8x squared plus 2 over 2x cubed plus x. There's my final answer there. Okay. Now, I talked about some notation before. Just a quick more example, and then we'll be done. I just want to show this so we can do some problems in class on it. It's kind of fun. What if they said h of x equals, how would we read that? Well, I'd read that as f to the fourth of x. Find h prime. Well, again, we have to think about what that means. F to the fourth power of x. That means f of x raised to the fourth power. When we write it like that, it's easier to identify, oh yeah, f of x is my in, x to the fourth is my out. So h prime then would be the derivative of the outside with respect to the inside times the derivative of the inside. Okay. Now maybe f of x has a graph and you can figure out, right, h prime of specific numbers by going off of a graph or a table or something like that. But that's how we can work those type of problems. All right, that's it for today. I will talk to you guys. I'll see you in class on Thursday. Take care. Bye.